In this lecture, I want to talk about reactions in the gas phase. For reactions in the gas phase, that is to say for reactions in which all species are gaseous, we can use partial pressures of the gases instead of concentrations to make a different form of the equilibrium constant, and we call it Kp. Let me give you an example. Gaseous dinitrogen tetroxide decomposes to 2 moles of nitrogen dioxide. Okay, so we can write an equilibrium constant based on the partial pressures of the gases. I'm going to call it K sub P. And the partial pressure is used in place of concentration. So it's the partial pressure of the products, so the product here is NO2, raised to the power of their stoichiometric coefficients. Okay, so this is the partial pressure of NO2 squared over the partial pressure of N2O4, and that would just be raised to the power of 1 because that's the stoichiometric coefficient of N2O4. Now, we could also write a regular K for this reaction based on the concentrations of each species raised to the powers of their stoichiometric coefficients. So, what is the difference between K and Kp? Well, we can derive an expression that relates them. Sometimes K and Kp are equal, but not always. It depends on the stoichiometry of the reaction. Let me show you what I mean. So we know PV equals nRT, ideal gas law, right? I could rearrange PV equals nRT to say N over V equals P over RT. Now, N over V is the concentration, right? Moles per liter. This is a concentration. Let me get rid of these parentheses because we don't need them. So concentration equals P over RT. So we could take this P over RT and substitute it into the expression for K. So here, K is equal to NO2 squared times N2O4 squared. And if we substitute P over RT into that equation, we get the relationship that the partial pressure of NO2 over RT squared over the partial pressure of N2O4 over RT. Okay, that's just substituting P over RT into the expression for K. So I want us here, I'm going to move this over. I want us to take a critical look at this for a second and see if there's anything we can do to simplify it. So let's separate out the partial pressures from the RT, because that will enable us to simplify this a little bit. This is going to be equal to the partial pressure of NO2 squared times 1 over RT squared over the partial pressure of N2O4 times 1 over RT. Okay, I'm just pulling out the 1 over RT. Now, what do you notice about this? Let's go up and look at the expression for Kp. So by doing this, this part of the equation is actually equal to Kp. And I can cancel out, so let me get rid of that for a second. Notice that I can cancel out one of the 1 over RTs like that. So for this particular reaction, K is equal to Kp over RT. Now, that holds true for this particular reaction, but this depends on stoichiometry. So we can make a general statement that applies to all reactions that relates Kp and K. Kp is going to be equal to K times RT raised to the power of what I'm going to call delta N. So this is the general statement that's true. Now, delta N is the sum of the coefficients, the stoichiometric coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. That's a mouthful. So if I use that relationship, I can calculate Kp from K and vice versa for any reaction just by looking at the reaction's stoichiometry. Let's do an example. Here, in this example, an equilibrium mixture contains 0.60 grams of solid carbon, as well as carbon dioxide gas and carbon monoxide gas at partial pressures of 2.9 and 2.6 atmospheres, respectively. All of this is at 25 degrees Celsius. From that information, can we calculate both Kp and K? Here is the reaction. Solid carbon plus carbon dioxide is in equilibrium with 2 moles of carbon monoxide gas. So looking at that reaction, we can write an expression for Kp. We leave the solid out of it. Kp is equal to the partial pressure of CO squared, okay, because of its stoichiometric coefficient, over the partial pressure of CO2. We're leaving carbon, solid carbon, out of it because it's a carbon, so it doesn't, it's a solid rather, so it doesn't appear in K. Now we know the equilibrium partial pressures from the problem. CO was 2.6 atmospheres, so I'm going to square that in the numerator. And CO2 was 2.9 atmospheres. So we calculate a K of 2.3 for this reaction. Now, that's the Kp. What's the K? Well, we can relate K to Kp using the relationship that we just talked about up here. I'm just going to rearrange this equation to solve for K. K is equal to Kp over RT raised to the power of delta N. Now, what is delta N? Delta N is equal to the sum of the coefficients of the gaseous products, so that would be 2, minus the sum of the coefficients of the gaseous reactants, so that would just be 1. So delta N here is equal to 2 minus 1, or 1. So that means that I can get my K by taking the Kp, which is 2.3 atmospheres. I'm going to leave out the units because K is generally unitless. I'm going to divide that by R times T. So this is 0.08206 liter atmospheres per mole Kelvin. That's the gas constant. Times T, which I mentioned this is at 25 degrees Celsius, so that would be 298 Kelvin, raised to the power of delta N. And delta N is 1. So this is raised to the power of 1. So this is the setup to calculate K from Kp. Now, when you do the arithmetic here, you will see, I'm just moving this over a little bit, you will see that K is not equal to Kp. K is equal to 0.094. I will leave that unitless. So you can see that in this case, K is not equal to Kp because I don't have the same number of gaseous products and reactants on both sides of the reaction. The only time that K is going to be equal to Kp is when I have a delta N of 0, because anything raised to the 0 power is 1, and you would get rid of that RT denominator.